Dr. Fizz here, Chapter E, our second big theorem for today, Stokes Theorem. Here we have part of a Maxwell equation, and we can consider this magnetic field B to be a general vector field, and we're doing a general problem where we integrate along a line that encloses on itself. So for this contour line integral, I have set up a nice simple case to analyze where the magnetic field or the vector field is in the plane, xy plane, and I'm looking at a lower left point where I have the magnetic field or the vector field in the x component being b sub x, x, y, and z, and b sub y, x, y, z. Over here, if I jump over to delta x, I'm going to look at a y component at x plus delta x, and if I jump up here I have a component with the y plus delta y. Notice here that there's always a bx and a by everywhere, but when you do your line integral you take a dot product, and the line integral has a differential dx on the bottom I hat. So I really don't care about the b sub y because it's a 90-degree angle with respect to the I hat. When I take the dot product, I want the component of the magnetic field or the vector field that goes along x. Similarly here, when I go along the y direction plus j hat, I want the y component of the vector field. Here, notice there'll be a minus sign when I do my integral because I'm fighting the flow. I'm going to the left, which is in the negative I hat direction. So when you have this b dot dl, b dot dl will be positive on the bottom, positive going up, and notice it'll be bx here and by here, and then here it'll be negative because the dl is a negative dx I hat, and here a negative dy j hat because I'm pointing down. So let's go ahead and work this out, and we have for the lower leg we have b sub x at x, y, and z times delta x. That's 1/4 of the trip. Then here I have by at x plus delta x, y, z, and delta y for the trip, going with the flow. And here comes my first minus sign, bx evaluated x, y plus delta y, z, delta x, because I'm fighting the flow. And here's my second negative sign, negative by x, y, and z, delta y. And that gets us the closed loop integration. And here we rearrange the terms slightly. We want to have the one with the delta x subtracting on the right here one with just x, y, and z. So I have the y component set up for that. I've taken this piece here, slid it over to the front, and then I have the by with the delta y over here, and then for the x, delta x, 2 with delta x, I have this one here, which is a plus sign. I'm going to put it second with a minus, so 2 minuses cancel, and I can slide this one inside the bracket where it'll be negative. I want this set up because I like to have partial derivatives staring me in the face, like we saw that earlier, and we're seeing that again. So that's suggesting that you multiply top and bottom here by delta x to get that nice partial derivative. Look at that, delta x plus delta x and minus, I think, with an x and over to delta x. And over here it has a y plus delta y and a y, so if you divide by delta y you got a partial derivative here. Multiply delta y so you don't change anything. And this is the secret in promoting a line integral to a surface integration. Analogous to our divergence theorem where we promoted a surface integral to a volume integral, like up in the dimension, here we're going to up the dimension of the line to the area. And these two theorems are kind of similar in that regard. So we come here to the result where we have our delta x in place and our delta y in place for their partial derivatives, and then you can see that this is going to lead, when we take the limit and do our integral, we're going to get the difference of partial derivatives over an area. And I'm emphasizing here with the a, capital A that I'm putting down here, that this a goes with this loop. This loop goes around a perimeter for some area that it encloses. So that's why I am emphasizing here the area of that enclosed region. Do you recognize that this is a z component of a cross product? If you have a cross product, A cross B, I had one teacher that showed me how to do this with a determinant. You set up I hat, J hat, K hat, and you put then the components down. And I had another teacher that did it without the determinant, saying, look, watch this trick. This is I hat, that's your X. So then you go A, B, Y, Z. And then you have a minus sign and flip the YZ on the A and the B. Then you have, next is J hat, and then you have to have cyclic. You have to have X, Y, Z if you go in a circle. So after Y comes Z, and then comes X, Y, Z, X, Y, Z. So that gets you that right sign. Then you put a minus sign and flip the indices on the A and the B. Finally, you have a K, you have a Z. What comes after Z is X, and then Y, and then you have a cyclic. And once when you get this, you put a minus sign and flip these indices. So that's another way to remember the cross product. Now the cross product with the del operator, it's neat that the del operator is used in this theorem in a different way with the cross product, and we use it earlier with the dot product. So if you do the same idea where the A now is your d partial derivative with respect to x, working on say here a BZ, you copy the BZ down, this would be the derivative with respect to y, and here you would copy the bx down and have the derivative with respect to z, because the a is being replaced by a differential operator. So instead of having a sub x I hat, we have the partial derivative with respect to x I hat. And here it is. This last piece here, the k hat piece, has the configuration that we need, and that is ideal because dx dy, where do you have your little unit vector pointing? It's pointing up, k hat. So because of that, we can write this as dx dy with the z component of the cross product, and we can get the z component of the cross product by considering the differential area element with the k hat, and then this z component that goes with this k hat, we can then write this as just the vector del cross b, that vector dot with dA, and what will happen here, since dA is k dA, it'll get us the right z. The z component will come off, the other two components will vanish, and this is Stokes' theorem right there, where we have promoted a line integral to an area integration of that area that's enclosed with this neat little trick.